Hugh is a colleague from the main engineering site. I won't say the main department because we're all part of the engineering department, but the main site. And he's a mechanical engineer, and he sort of sidled into this climate repair stuff and infiltrated all corners of it, doing some really exciting work here. It's a tremendous project, and the climate repair group is doing really great things, going from strength to strength. And so Hugh is now going to tell us something about it, not all about it, because he's only got until Buns time, which he's very well aware of. So welcome, Hugh.
Thank you very much, Claire. Yes, I've even put Buns in the title of my talk. So I want to tell you about the Centre for Climate Repair and the things that we do. It's a very entry-level talk, just so do ask questions afterwards, either here or over Buns, or even at other times. Our Centre for Climate Repair, based here in Cambridge, has three core principles. One is, of course, deep and rapid emissions reductions. We've got these three R's. So the first R is we've got to stop burning fossil fuels, and that's a given. The next one is greenhouse gas removal. That's the second R. We know that we've got excess greenhouse gases in the atmosphere, and they're going to stick around for centuries. We've got to turn that around. And the third one is right now we've got a significant short-term problem, an immediate problem, particularly in the Arctic and Antarctic regions. We've got to make sure that the ice there doesn't melt. Now, why is the Arctic so important? If we look at this picture of the globe, this was what's called the temperature anomaly. That's how different is the temperature from what it ought to be. And back in a century ago, this blue color, you can kind of see the color code on the left, meant that it was slightly below the average it's been over the last century or so. But then when we go back to maybe 20 years ago, things have got warmer, and we know that. And then when we go to quite recently, it's warmer even still, but the bit that stands out as being exceptionally warm is the Arctic. There is a curious blob here. I think that is indeed the technical term for that, which is all related to melting of ice off Greenland, but we can talk about that later. This is the situation here in Cambridge. I do have, I've got two versions of my card, which you can take when you pick up when you leave. One of them has got this this chart on it, and it is just really goes to show that over the last 150 years, well, this line here is the average from the for the last 60 years or so. For the last 10 or 15 years, we've been above average by about a degree. So it makes you think a little bit about what do we mean by average. And it really means, certainly for Cambridge, we ought to have been thinking for a long time of designing our buildings for the types of temperatures that we have today. Not entirely sure that that's been too successful, but there we go. The Arctic problem can be summed up in really four main points. One is about albedo, reflectivity, and ice reflects sunlight pretty well, and but open water is not so good. So if we lose ice, we lose reflectivity, and the word for that is albedo. The next is that if we do get warming up of the Arctic, underneath the Arctic is a lot of fossil, if you like, dead organic matter, which is poised to release a lot of methane, and methane is 80 times more potent a greenhouse gas than carbon dioxide. We don't really know what that might look like, but we're concerned about methane, which is growing as a greenhouse gas in the atmosphere. We know about melting causing sea level rise. These numbers get pretty ridiculous. Greenland ice shelf holds 2 million ice sheet, it should say, holds 2 million cubic kilometers of ice. You've really trying to get your head around these big numbers. But if it all melts, then we're in for a 7-meter sea level rise. And realistically, that's not going to happen in the next 100 or 200 years, but it might happen in the next 500 or 1,000 years. But we'd like to think that we're still around in that length of time. 2050 is not an objective in itself. And we've all seen weather patterns going completely crazy over the last few years. And that's all linked to the steady warming of the Arctic, changing weather patterns. If you want to visualize the Arctic ice problem, imagine, when you get home this evening or sometime over the weekend, you might sit down and have a gin and tonic or a Diet Coke or whatever it might have, and you might put some ice into it. And at some stage or other, you might say, hey, I could do with some more ice. And my guess is it might be sort of maybe sometime around this time. Well, this is the situation we are in with the Arctic ice. It's not we're not making this up. This is what's happening. Now, if you then plot that data, the red line here is the same as the red line down here. But the issue really is trying to do forecast. It's always a tricky thing. The random data, you think, well, how do I extrapolate? You can think these lines here, this is how much ice is there in the winter maximum, and this is how much melts. When these two are equal, we lose the sea ice, well, when might that happen? We don't know. But all I know is that in 100 years' time, none of us will be here, but our kids, grandchildren, great-grandchildren won't really care whether it's 2029 or 2035 or 2042. It was on our watch. So let's not get too fussed about the exact date. It's on the cards, so we need to be thinking about that. Now, we could say, well, let's just get off fossil fuels. But if we think about getting off fossil fuels, we need to think of how badly we've been doing that. This is the amount of carbon dioxide that's been generated annually over the last 150 years or so. And all sorts of things have happened, and yet it's not slowing down. Now, we've got to turn it around, and we've got to get down to zero pretty soon. But it's just not happening. Now, we might think, why isn't it happening? And, well, is it all my fault? If I think about the things that I can do, well, I try to recycle stuff, and I try to make sure that I pick up the poo from my dog, and I do all the right things. But if you look at the numbers here, the things that we try to do as individuals are of the order of hundreds of kilograms of stuff. I'm not talking CO2 here. I'm just talking about things that I can do. That's a scale of things that we're used to dealing with. But if you look at the number of here, this is 40 billion tons a year globally. And with world population being 8 billion, nice easy sum, 40 divided by 8, the billions cancel. The average for carbon dioxide emissions over the planet by individuals is 5 tons a year, which means it's a lot bigger than these sorts of things. So it means, but I can't see the CO2. Oh, it's a good example of not being able to see the CO2. If I fly to Melbourne, which is where I grew up, and it's the kind of thing that we do. We go and see our families, and I want to visualize the CO2 from my flight, because sure as hell the airlines don't tell me. So what I do is I imagine I've got a suitcase, 20 kilograms, and that 20 kilograms, we know what that feels like. It's a typical suitcase that you would check in, and it's got CO2, dry ice in it, 20 kilograms of dry ice. And my question is, how many of those do I need to pick up at Melbourne Airport when I get to Melbourne? So you can do the calculation. The plane I fly in is burning fuel. This is information just off the internet. The 4 kilograms per second. It's a 20-hour flight. There's 350 passengers, all round numbers. Each kilogram of fuel generates 3 kilograms of CO2. That's just because of hydrocarbons. The hydrogen is quite light, but the oxygen is quite heavy. So that's a bit of chemistry. And now I've got all the information I need to work out how many suitcases. So 4 kilograms per second, 3 kilograms CO2 per kilogram of fuel, 20-hour flight, 3,600 seconds in an hour, 350 passengers, 20 kilograms in a suitcase. I have to pick up 125 suitcases. Now, does anyone ever tell you that? They don't tell you that because they don't want you to know that, because it would be very inconvenient if everybody knew that. And that's just one way. So I've got to do the same when I come back here. And that's just for me. Every other passenger's got to do the same. We simply do not have in our minds the scale of the CO2 problem. We just don't, we're not interested in it. No one tells us and we're not interested. I just want to know if when my suitcase is going to come out, and hopefully quickly, and then I can go and enjoy my holiday. If I knew about the CO2, I want to enjoy my holiday. So what are our options? So this gets to the second of my cards. So you can decide which one you want, or maybe you would like both. There's this thing called the napkin diagram. And the napkin diagram was this guy, John Shepherd, in about 2010, was in a pub and he's just sketched this thing. And he said, you know what, it's not that complicated. Over the next couple of 100 years, business as usual, burning fossil fuels. And that's the line we're on. This is not a made-up line. If you actually look at the gradient of that, that is the rate at which we're burning fossil fuels. Business as usual is going to send us up to 6 degrees in the next century or so. That's just what's going to happen. So what we've got to do is to stop burning fossil fuels. Now, this is a guess, but the best estimates are that, through the COP process, through the Paris Agreement and all that, that we're just not going to achieve this magic thing called net zero by 2050. Just not happening. But if it does, that's great. But I think we should be prepared for it not happening. So net zero means we're stopping burning fossil fuels, which if we manage to do that, that's this blue curve here. The thing is that the carbon dioxide stays in the atmosphere for 1,000 years. So this reaches a level, it doesn't start coming down very quickly. Carbon dioxide removal we have to do, planting more trees, machines to suck CO2 out of the atmosphere, enhancing ocean carbon dioxide uptake, all of that. But let's suppose we do both of those things as rapidly as we can. And this might seem pessimistic, but looking like it's going to take us another couple of 100 years before we really get stuck into it. In the meantime, there's this thing called solar radiation modification, which we have to do in addition to carbon dioxide removal and emissions reductions to keep temperatures down to today's 1.5. And many would say the 1.5 is already too high. So what do we mean by solar radiation modification? And this is at the center of the things we do in our Centre for Climate Repair. It's reflecting a bit of sunlight. Maybe 1% of today's sunlight reflected would cool the Earth by a degree or two. How can we do that? Well, we can surface albedo. That's the kind of things we're looking to do in the Arctic. We can make clouds whiter. That's marine cloud brightening. We can try to change the chemistry of the stratosphere. That's up at 20 kilometers. We know that volcanic eruptions have done that in the past. And we can also do wacky stuff, space-based methods, which 10 or 15 years ago I would have thought was completely ridiculous. But now we see the kinds of things that SpaceX and Elon Musk and so on are doing. Maybe they're not so ridiculous. So I'm going to kind of talk through some of the things that we do at our Centre for Climate Repair. The overview of sunlight reflection methods, SRM, really covers these sort of green ones, the ones that are over here, reflecting sunlight by various methods. But there is a whole lot of other things that we're interested in about removing carbon dioxide, in particular ocean fertilization, because the oceans are a huge sink, potential huge sink, and we need to try to enhance that. Now, the biggest thing that we're doing, John Taylor and his team in the Department of Applied Maths, is looking at kelp and kelp farms, if you like. One of the issues, though, is that you can grow kelp, seaweed, but then when it dies, it might only sink a short distance before it kind of gets recycled by fish and other organisms, and the CO2 might be taken up by the oceans for a bit, but the time scale for this is maybe 10 years. If we really want to sequester CO2, we've got to figure out how to get the dead kelp, the dead seaweed, down to quite deep. We've got to get to the area where it's so dark, what's called the midnight zone, where things don't really live anymore. And that means that we've got the order of 1,000 years, we don't quite know, of sequestering. But we're trying to figure out how to do that. It's not obvious. So anyone who says all we have to do is to fix the oceans, it's not obvious, which is why we need to do the research. The area that I was working on about 15 years ago was a thing called the SPICE project, Stratospheric Particle Injection for Climate Engineering. And this is looking at the things we had learned in 1991 by measuring the eruption of Mount Pinatubo in the Philippines. And volcanic eruptions are not very nice things. They're not very friendly things. A lot of people die. They're disasters. But what we did notice with the eruption of Mount Pinatubo was over the next 12 months or so after the eruption, there was a cooling of the Earth by maybe half a degree, 3/4 of a degree, over a period of about a year. So that made a lot of people think, well, if we're concerned about climate change, could we artificially create a Mount Pinatubo? Now, what you want to do is avoid all of the rock and ash and dust and all that crap. That's nasty. But inside the eruption were these volatile components, in particular sulfur dioxide. And sulfur dioxide, a gas, would get up into the high atmosphere and change the chemistry of the stratosphere, the high atmosphere, to produce tiny little droplets of sulfuric acid. And you can kind of think, God, we don't want to be putting sulfuric acid in the atmosphere because we've spent so much effort getting it out, acid rain and all that. But unfortunately, life's a bit like that. We've all had decisions in life where you make a decision and then you regret it because you really not really thought it through properly. Well, that happens all the time in life. So what we noticed that this was what a high altitude image of the atmosphere before the eruption of Mount Pinatubo and afterwards, and very clearly the optics of the atmosphere has changed. So then the question is, how might we go about? Then the question is, how might we go about doing an artificial Mount Pinatubo? So for our SPICE project, Stratospheric Particle Injection for Climate Engineering, we were looking at, well, maybe we could fly aircraft up high and release some sulfur dioxide or other materials, or airships or tall towers. But the technology that we were quite interested in is the idea that we could have a balloon tethered up at 20 kilometers with a strong composite pipe, maybe this sort of size, up which we could pump of the order of 30 kilograms per second of stuff. Now, 30 kilograms per second, what does that mean? Well, Formula One is quite handy when they put those refueling tubes onto the side of the car. They can get 50 kilograms of fuel into the Formula One car in a couple of seconds. So we're not talking about numbers that are crazy, but they're pretty crazy. The craziest bit is doing this up to a height of 20 kilometers. This diagram's not to scale, by the way. This is just to illustrate that we'd probably do it in tropical regions because that's where the sunlight is strongest. So we're talking about this up at about 20 kilometers. This would have to be quite an interesting bit of technology, but that's what the research is all about. So everything was going great with this project, but then anybody who thinks that oh well, we can solve the climate problem by getting off fossil fuels, a lot of people are very concerned that any talk at all about climate repair or about geoengineering, as it's often called, is a distraction. And particularly, they'll pick up on anything. And one of the things that back then we were funded by the EPSRC, and the EPSRC was saying, we really want you to file for patents in this technology because that's what engineers do. But you know, at the heart of the problem was that we'd filed patents because we were asked to do it. Anyway, our project got cancelled. And that was the first of quite a few projects over the last 10 or 15 years that have got cancelled for one reason or another. It's a bit annoying. I mean, the thing that really annoyed me about this particular New Scientist article is if you look at this picture and you imagine which way the wind is blowing, I kind of think, you know, if a science magazine, you know, if the wind's blowing that way to push the balloon, then why is this going? And when I spoke to Michael Marshall, he said, oh, well, I didn't have enough space on my page to do it. Anyway, it's a bit frustrating. But we were, the general view seemed to be that anybody working in this area was either being paid by the fossil fuel companies or were somehow evil in some way. But this was our team. And I mean, we might have had a drink or two that night, but we're not evil people. We are trying to work towards a solution to this rather difficult problem. Some of you may remember Chris Burgoyne. Sadly, he died 2 or 3 years ago. Really sad to have lost him. He was a great member of our team. What other things are we interested in? This is an ice-thickening project, which Sean Fitzgerald is leading. And this work is going on as we speak. And the idea is that you might have floating sea ice. This ice here may be only 0.5 meter thick. And you pump water up from underneath and you pump it onto the surface and you flood an area of the surface. Now, what's interesting about this is that this here is snow, and snow is quite insulating. So when you pump the water on, you're not pumping the water on there to make the ice thicker. You're pumping the water on to solidify the snow. Now, if you know a little bit about heat transfer, you can kind of think, well, I've got this 0.5 meter of ice. Ice is not a great conductor of heat anyway, but the snow is a really good insulator. Get rid of that insulator. It means the minus 40-degree air up here can now, the coolth, if you like, can conduct more readily because the water underneath is at 0 degrees or minus 2 degrees salty water. If you can increase the heat transfer through that layer, then you can increase the rate of ice thickening underneath. Now, the fun thing about this technology, do go and have a look at it on the internet. It's pretty cool. Rather than trying to put the pumps up on the surface, what they're doing is they're devising these underwater drones, which go in underneath the ice, and then they'll drill a hole up from underneath, poke up, pump some water, and then they'll do that for a few hours, and then they'll come down, and then they'll go over here and they'll do that again. And then once they've done that a few times, and then once the batteries run out, they'll go off to some mothership somewhere, recharge. And so where the energy comes from, that's a tricky one because it's got to be done in the dark of the winter. So solar power is not an option. Maybe wind power, or maybe small modular reactors, or who knows. But this is a ice thickening project, which is really very interesting. It's not clear at all whether it's scalable, but it may be very useful for regions where they really need to maintain their sea ice. Another area which is very interesting to us is what's called marine cloud brightening. A lot of these technologies have three-letter acronyms, and marine cloud brightening is no exception. What we know is that these are called ship tracks. So satellite images of large commercial ships moving across the Atlantic or the Pacific would leave behind these trails of clouds. And that's because in their rather dirty exhaust from their engines going up the chimneys on these ships, the particles would nucleate clouds. Now, rather strangely, back in 2020, the International Maritime Organization stipulated that fuel in ships should be cleaned up. So now there's not much sulfur in shipping fuel anymore, which is the right thing to do to get rid of sulfur, to clean up the air, particularly around ports. But now we don't have any of these ship tracks anymore, and clouds are quite good at reflecting sunlight. So the question then is, can we recreate the effect of ship tracks? And it turns out that one thing you can do is you can take seawater and pump it up and spray it out. And they're doing this in the Great Barrier Reef in Australia. You pump it out and you spray a fine spray. And this is kind of like what nature does already. When there's a storm, you get a spray of seawater spray. And so Dan Harrison, who's got a very broad Australian accent, I'm afraid the sound isn't working here, but never mind, I can do the best I can. Right, so Dan Harrison is telling us about the spray just near the Great Barrier Reef in Queensland. And so the idea is you produce a spray which is as fine as you can make. The spray is of seawater, but it dries out into saltwater crystals. So over here, it's more or less dried out, and those saltwater crystals make their way up to cloud height, where they nucleate clouds. So these clouds here, there's obviously water vapor up there, but there's just not enough nucleation sites for the clouds. So this marine cloud brightening field work that they're doing is really interesting. What we're doing in Cambridge is investigating closely how we generate these droplets and to reduce the amount of power required. Because unfortunately, this technique is probably not scalable at the moment, just because the ship needs, this particular boat needs 150 kilowatts of power to run the sprayers. They're doing a lot of fun work with drones flying through the plumes, and so we're doing some of that drone work as well. It's a lot of fun. It's really important to engage with Indigenous people, because you can't just walk onto people's turf and say, "Hey, look, we're gonna do stuff here. I hope you don't mind." They've done a fantastic job right from the very beginning of this project, engaging with the First Nations Aboriginal people who live and fish and survive around the Great Barrier Reef. The work that we're doing in the Arctic, likewise, is we're engaging directly with the local Indigenous people up in northern Canada. Sean Fitzgerald, who's just come in, director of our Centre for Climate Repair, might be able to tell you a little bit more about that afterwards. But now, at the beginning, I did say I was very skeptical of these reflectors in space idea. But there's a guy who came to our conference last year and he gave a talk. And he used to work with SpaceX, and he's now set up this thing called the Planetary Sunshades Institute. And boy, when you talk to him, he just says, look, this is not difficult. We've just got to have everything, whatever we choose to do for the climate is going to be difficult. What he says is that between the Earth and the Sun, there's this point called L1, the Lagrange point, the first Lagrange point. And it was Lagrange, the mathematician, who came across this. It's where the gravity of the Earth is equally balanced by the gravity of the Sun. So can we put stuff there? And then one of the catches is there's a strong solar wind. So you kind of have to put it maybe a little bit closer to the Sun. And it turns out, for rather curious reasons, you can't just keep things still there. You've got to go, you have to orbit. You've got to orbit this L1 point. But they've done a lot of sums and a lot of thinking about how you would deploy and get this thing to the right place. But one of the neat things is that people will say, oh, well, what if it doesn't work and it goes wrong and it'll be there for centuries? Well, it turns out that if you leave it by, it's just going to, and the sun's gravitational pull will pull it into the sun. You have to work quite hard to keep these things there. So like a lot of good technologies, if they go wrong, they'll naturally dissipate in a couple of years. So I've kind of given you a whistle-stop tour of our Centre for Climate Repair, and I hope it scares you a bit that we're even thinking about this, because the fact that we are thinking about this seriously, and the fact that the UK government is putting in at the moment £60 million of research funding through this new ARIA funding body. The fact that we are thinking about this is a good thing. It's not a distraction from getting off fossil fuels, because we've just got to get off fossil fuels, but it's a necessity. So thank you all very much for your attention. I'm happy to take questions. We decided, Claire and I decided that these are called PBQs, pre-bun questions.
As you were mentioned, do you want to say?
I can do, but
You need to come over here because there's a microphone here. So this is.
I can do, but clearly I'm feeling a bit exposed because I missed the first 25. So really, really sorry about that. But you did mention ice thickening. The ice thickening project, just to reinforce Hugh's point about how you do work outside, does involve a lot of work with the local indigenous people. And if you work in the Arctic, you may have heard of a term called free, prior, and informed consent before you do anything. My own personal view is that is the bottom rung of the ladder. And whilst I will accept it is necessary and it's the bare minimum, it is the bare minimum. And I actually think it's inadequate. I think you need to do way more than that, which means actually including, you saw the indigenous person on the boat at Marine Cloud Brightening, you need to include people in the research, which means making sure that they help shape the research in the first place. So you co-develop, co-curate, and then actually pay them to be part of the research team, not just for one season, for multiple seasons, so they're integrated. They've got so much knowledge that we can learn from. It's very much a two-way process. It's not a single-way process. They've got a huge, the reason why I think they've got like 50 words for snow is that there are 50 types of snow. And that actually what you think about putting water onto ice covered in snow is non-trivial. And they've got all that knowledge about living and working in those conditions. And then ultimately, the people that will lead any activity in the longer term will be them. So this is actually a whole process, and free, prior, and informed consent is just the absolute bare minimum, the first rung of the ladder that we need to be thinking about as we progress research. Yes, sorry.
Oh yeah, so
I'm very curious.
yeah, we're all very curious. It's interesting. The big blob. I think it's if you look it up, it's called the warming. They rather perversely call it the warming. It's the ocean circulation. There is a thing called the AMOC, the Atlantic Meridional Overturning Circulation, and there's a huge circulation of water around the whole planet, and it's driven by temperature and salinity. And what seems to be happening is that that circulation has been disturbed in this region. So what should be happening is that cold fresh water. Now, salt water is dense and cold water is dense. So cold fresh water, in the battle of which is more dense, over the last thousands of years, that circulation is established. And that cold fresh water would sink. But now at that point, it's surfacing. If you look up AMOC and collapse of the AMOC, right now, jury's out as to whether it's a disaster which is going to happen in the next 50 years or the next 500 years. But it's looking pretty rocky. Other questions? Yeah.
I have a question. So these interventions you talked about, how long do you reckon it would take until they actually, if they work, how long would it take to get to the point where they can?
So the question is, firstly, the statement, I am scared. I'm saying this for the microphone. But how long will these interventions take? The first thing to consider is, supposing we had all of a technology available at scale right now, then you could deploy them if you could right now at scale, and they would have immediate effect. It really is exactly like putting up an umbrella, and it would cause cooling straight away, and the climate would respond immediately, of the order of months, years, months. The Mount Pinatubo, for instance, erupted, and there was cooling immediately in the months. But the scale that we need to do things on is, Mount Pinatubo was about 30 million tons of sulfur dioxide. Now, 30 million tons might sound a lot, but it's nothing compared with the 50 billion tons of CO2 we're putting in. It's taken us the best part of a century and a half to get our CO2 output up to 50 billion tons. To get our SO2 output up to the right level, if we really work on it quickly, we could perhaps do it in 10 or 15 years. But think of governance, think of opposition. And my guess is that in the Spice Project was 15 years ago, and where are we now? We haven't got any further at all. All down to political will. Money, we're getting the ARIA, the Advanced Research and Invention Agency, has put 60 million into all of this work. But you can't even buy a Premier League football player for 60 million. It's peanuts. So it comes down to a will to do it. I can see Sean wants to say something on this.
This is just to recap on the I'm scared, and we are too, but we're scared for multiple reasons. We're scared about the future without even thinking about these sorts of things, about where society's going. And it really just being, I mean, look, I'm not wearing shorts normally, but, you know, I'm wearing shorts by trying to be sensible in this very hot weather. And this is going to become more of the norm as we go forward. And what does that mean for wider society in the next 50 years? Where is society going with seemingly unchecked emissions unfolding? We talk about emissions reduction. How many years have we been reducing emissions? I mean, we've been talking about it for 31 years. We're spectacularly failing. Anyway, so we're scared for that. But I don't like the idea of this either. In other words, the whole concept of it seems scary, but we need to evaluate about which is the least scary. I don't think there are any non-scary options.
Other questions? Yes, we've got one here.
It's kind of pushback. People you might want to keep the North Passage open, or create a North Passage.
So the question is, are we getting pushback, political pushback? There is, of course, some advantage for the fossil fuel industries and perhaps for certain countries to be able to sail ships through the Arctic, to be able to drill for oil. Yes, that's alive and well, and we personally don't get that, but it's certainly it's a big issue. I think people are just in the last few years, the negativity that we used to have a lot of hasn't gone away, but it's just 2-3 weeks ago there was a front page headline in the Times saying that people were pretty comfortable with the idea of research into this. Boy, 5 years ago we would not have had that headline. But there are also colleagues of ours who think that that headline itself is dangerous because it lets the fossil fuel companies off the hook. It's a complicated thing, but it's a good question. Other question? Yeah.
Really enjoyed the talk. I enjoyed the visualization of the mission for flight Melbourne. But there's been a lot of interest in sustainable aviation fuel. I'd love to hear your thoughts on this.
Yeah. So the question is about aviation fuel and whether, so aviation at the moment worldwide is perhaps, in terms of emissions, maybe 2% of carbon dioxide emissions. But then there are other factors to do with contrail formation and to do with the fact that emissions at sea level have a different effect than emissions high up. You could argue that aviation is 5%, but it doesn't really matter. It's a small figure, but it's a hard to abate sector, because if you want to fly from here to New York, find a battery aircraft, but they're sort of 12-seater aircraft, and you'll be able to fly probably from London to Paris in a battery plane, is my guess, 12-seater. That's where we're at the moment. Maybe the hydrogen economy, that we were just talking about this before, maybe that will move forward, but it's not going to happen anytime soon. Can I just say that the emissions from the flight are one thing, but it's your lifestyle. If you are one of those people, a small proportion of the world's population can afford to fly. If we're all here above average, we're way above average. I would venture to suggest, in terms of income, we are all in the top 1%. No matter how poor a student you might think you are, we're in the top 1% of the world's spenders. And flying is an indication that that's where. So it's not just the flying you've got to stop doing. It's so much. But so aviation is going to be a hard to abate sector.
The magic hour has come.
It has.
So thank you very much. Thank you for wonderful questions. Keep talking in the common room. There are a lot of locals, cake, treat yourself, tea and coffee.
I do want to say just one last thing, which is the reason I wanted to come here and talk to you is that I just wanted to make sure that you know that this work is happening. And some things, if you want to be involved, speak to Sean, to Emma, to Roweda, to Dante. But also, if you're an academic and you want to get involved in supervising PhD students or applying for research grants, we need you. So thank you very much.